Alright, here are the second set of solutions to the practice test. Number 14, a 5 kilogram bucket of water is swung in a vertical circle. What's the minimum speed so the water doesn't spill? So, at the top of this loop, you've got two forces pushing down, gravity, as well as the tension in the string. However, if we're talking minimum speed, that tension is going to be zero. You're basically swinging it so slow that the string is no longer pulling down at the top. The water is just barely, because of inertia, barely continues around its path. Which means the only force pulling towards the center of the circle is gravity. So it's your centripetal force. So mass times 9.8 equals mv squared over r. So this 5 kilogram bucket, we didn't even need to know that. You just put any mass. Doesn't matter. Solve for v. Square root of gr. Do that, you got 3.6 meters per second. Number 15, the pendulum reaches a speed of 4 meters per second at the bottom of its swing. What's the tension? So at the bottom of the swing, you've got force of gravity pulling down. You've also got force tension pulling up. At the bottom of the swing is where the tension is the most. So our centripetal force then is tension minus the force of gravity. So we got mv squared over r equals this tension force we're solving for minus mg. Notice we cannot cancel the m's because there's no m in the ft term. So you just plug in all of the information you know. Mass is 3 times speed squared divided by the 1.2 meter radius equals out to minus 3 times 9.8. Do your algebra. 69.4 meters. 16. The car runs a flat 85 meter radius circular section of road at 20 meters per second. What's the minimum mean for the car not to slide? So, your force towards the center of the circle, your centripetal force, is friction. So mv squared over r equals mu times the normal force, which is also mg for this car because it's on a flat surface. Cancel out. So mu, if you move the g to the other side, is v squared over gr, which is 0.48. 17. A pilot in a plane performs a vertical loop with a radius of 700 meters. At the bottom of the loop, it's going 210 meters per second. That's the upward force on the pilot. So at the bottom of this loop, there's two forces pushing on the pilot. There's this upwards force from the seat, we'll call it a normal force, and there's the force of gravity pulling the pilot down. The centripetal force would be the sum of those two, where the normal force is pointing toward the center of the circle, gravity pulling away. So 1v squared over r equals the normal force, which we're looking for, minus mg. Plug the mass, the velocity squared the radius, and 9.8, and you get a normal force of life, 4,732 newtons, which, in significant figures, 4,700. 18, a ball is attached to a string, swung horizontally. What path will the ball follow the instant the ball breaks, or the string breaks? So our circle is going around, let's call it clockwise. As it breaks, it's going to fly tangent to the circle, which is path 2. Number 19, 65 kilogram student is in a car traveling 25 meters per second on a hill of radius 110. So here's your hill. Here's your car, driving along. The person inside of the car has a normal force pushing up on them and a force of gravity pulling them down. Now, why did I draw force of gravity greater than the force normal? Well, if they were equal or if the normal force was bigger, the student would either fly up out of the seat or the car would lift up off of the ground. Something weird would happen. So our centripetal force on the student is the force of gravity minus the normal force. You might be asking, why is the force of gravity considered positive? Well, if the center of the circle is down here, any force towards that center we call positive with these circular problems. So we got mv squared over r equals g minus fn. put in your mass of the student, your velocity, your radius, and you get a normal force of 267 newtons. Number 20, which of the following is a free body diagram for a person on the gravitron? Well, this person has a normal force from the wall pushing out on them, gravity always pulling down, and friction on the wall holding them up. 21. A satellite is in stable circular orbit around the Earth. Another satellite is in orbit at greater altitude. What do we know about the speeds and period? Well, first of all, for any satellite, the centripetal force is the force of gravity. So, G M N over R squared equals M squared over R. One of the R's cancels out. Mass of the Earth, mass of the satellite cancels out. So if you solve for the velocity, this orbital velocity, if you want to call it that, you would get G, mass of the planet, let's call it Earth, over R, take the square root. So if we have two satellites, one's with a greater radius, the bigger this R value is, the slower it can go, and the longer period it will have. Therefore, if this other satellite is at a greater altitude, it's going to be going slower and have a longer period. Number 22, Oberon is a satellite of Uranus. It has an orbital radius of 5.83 times 10 to the 8th meters and an orbital period of 1.16 times 10 to the 6 seconds. What's its the mass of Uranus? So we already determined in the previous problem that your orbital velocity is g times the mass of the planet divided by r, and you take a square root. We also know that its orbital velocity is 2 pi r divided by the period. So if we set those two equal to each other, 2 pi r over t equals g mass of the planet over r under the square root, we can solve for mass of the planet by doing some algebra. Square on both sides, then multiply by r and divide by g. You end up with 4 pi squared r cubed over t squared g. Plug in all your variables carefully, you get 8.7 times 10 to the 25 kilograms. Number 23, a certain planet has a mass of such and such and a radius of such and such. What's the acceleration due to gravity on that surface of the planet? So Fg, so gravity equals g, mass of an object, any object on that planet, times the mass of the planet over r squared. And if the force of gravity on that object is the only force on the object, it's really mass times acceleration equals g and m over r squared. Remember, this is like the problem we did in class where an astronaut's standing on Mars and they drop a ball, and you want to know what's the acceleration. Well, the only force is the force of gravity. So that's the net force, it's ma. So if you cancel out the m for the object, you're left with the acceleration of the planet. A equals gm over r squared. And g, mass of the planet, divided by the radius squared, and you get 3.25 meters per second squared. Shows B. 24, which of the following shows how force of gravity varies with distance of separation? In other words, radius. These two are related inverse squarely. Choice D. Number 25. The Earth pulls on the Moon with a force of 2.1 times 10 to the 20th newtons. The Moon will pull on the Earth with a smaller force because it has a smaller mass than the Earth. This is false. They pull on each other with the exact same amount of force. It's just that the Moon's mass is so much less than the Earth's. We don't notice the Earth moving towards the Moon. We notice the Moon orbiting the Earth. We do feel the effects of the Moon's gravitational pull on the Earth. We see it in the tides. Number 26, very similar to a problem we just did. It gives you the period, the radius, and it wants to know which planet, so we're identifying it based on its mass. So again, the orbital velocity is g times the mass of the planet over the square root, and also equals 2 pi r over period. So by setting those equal to each other, we can isolate MP. It's going to be equal to 4 pi squared r cubed over t squared g. You don't have to solve it by going through the algebra and getting everything on one side. You could do it with numbers all along. I just prefer to type in the numbers once at the very end. It's up to you. By doing this, you get 5.66 times 10 to the 26 kilograms, which is alright, last problem, 27. Okay, fighter jet is practicing a loop-loop maneuver. The jet makes a vertical loop with a diameter of 600 newtons. At the bottom of the loop, it's moving at 150 meters per second. What's the normal force on the pilot? So at the bottom of the loop, you've got a force of gravity pulling down, and you've got a normal force pushing up. This is the place in the loop where there's the most normal force, because you've got your force of gravity fighting against, and so you need the same net force all the way around the circle. So your centripetal force is equal to the normal force minus the force of gravity. So mv squared over r equals fm minus mg. Plug in the mass, the velocity, and the radius. You get a normal force of 3,784 newtons. So he's feeling the pilot, he or she is feeling quite a bit of force pushing up. To give you some context, if they were just standing on Earth, 80 times 9.8 is just 784 newtons. So, huge difference between these two. If they're standing still, it's 784. If they're flying in the bottom of this loop, then all force pushing up is, approaching 4,000 newtons. So, huge amount of force pushing up. So this is going to cause a big acceleration on the pilot. So the acceleration is v squared divided by the radius. And you just do 150 squared divided by 600. It gives you an acceleration of 37.5 meters per second squared, which doesn't sound like much, but when you turn it into g's, divided by 9.8, this is 3.8 g's. Okay, that's going to be tough for an average person to withstand. Pilots, I'm sure, are fine with it, but still nothing to roll your eyes at. I hope that seeing these solutions helps you prepare for the test on Friday. Sorry I wasn't able to be there this week, but life calls, gotta be there when your kids are born and take time to be with family. Good luck, and I'll see you next week.